students, how are you all? So today we are going to discuss a very important atomic structure, and that is Bohr's atomic model. Niels Bohr was a Danish physicist, and he had made remarkable contributions to understand the structure of atom. And his work has also received Nobel Prize in the year 1922. And today we are going to discuss this very important structural model of atom named as Bohr's atomic model. So students, let us now discuss the important postulates of Bohr's atomic model. He stated that electrons revolve around the nucleus. Electrons revolve around the nucleus in well-defined circular paths of fixed radius and energy. So it was just proved by the Rutherford model of atom that inside the atom there is a positively charged region known as nucleus. He said that the electrons are revolving. Electrons are revolving in circular paths of fixed energy and fixed radius. The electrons are revolving in these circular paths, and these circular paths have fixed radius as well as energy. The circular paths are known as orbits, and these circular paths were named as orbits, and the energy and the corresponding energy state of the electron is known as stationary energy state. For an example, let us just take an electron here. So the electron in this state, the electron in this energy level will have a particular kind of energy, a particular amount of energy it will have, and that particular amount of energy will be called as the stationary energy state. So stationary energy state simply refers to the level in which the electron resides, the energy level in which the electron resides. So this is the first postulate of the Bohr's atomic model. The second postulate is the energy of the electron in its orbit does not change of its own, which means that there are various energy shells around the nucleus. The first energy shell is named as n equals to 1, or it is called as K shell. The second energy shell n equals to 2, or it is called as L shell. And the third energy level, that is n equals to 3, and it is called as the M shell, and the same thing will follow further and further. It is stated that if we have an electron in the energy level 1, we considered as energy level 1 n equals to 1. If the electron is residing in the first energy state, then it will not gain or lose energy on its own. It will have a fixed amount of energy, that is, the energy of the electrons is quantized. But when a sufficient amount of energy is supplied to the electron, then the electron will gain energy, and after gaining energy, the electron will be excited to a higher energy level corresponding to the amount of energy absorbed. Let us say that the electron residing in the first shell has absorbed enough energy to be transmitted to the second energy shell. So this is the case here. While being in its own energy state, it does not gain or lose energy, but if it gains energy from the outside, then it will be excited to a higher energy level. From a lower energy level, it will be shifted to higher energy level after gaining some sort of energy. But the higher energy state is always unstable which means that it cannot accommodate that energy gain for a long time. It has to lose energy, and after losing energy it will be brought back to the same energy level. If the energy of the lower energy level is E1 and the energy it absorbed from the outside and its energy has become E2, then it will be shifted from the lower energy level E1 to the higher energy level E2. So what change happens there is the change in energy can be represented as E2 minus E1, means energy of the higher energy state minus energy of the lower energy state, that is the change in energy. So it is quite clear that the electron, while being in the same energy orbit, does not gain or lose energy. If it gains energy from the outside, then corresponding to the amount of energy absorbed, it is excited to a higher energy state when it absorbs energy. And after losing the same amount of energy, it is brought back to the lower energy level. It is now clear that when electron gains energy, it is shifted to the higher energy state, while when it loses energy, then it returns back to the lower energy state. Now the thing which is important to note here is the energy emitted by the electron is seen in the form of electromagnetic energy, and when the wavelength is in the visible region, when the wavelength is in the visible region, it is visible as an emission line. Look at the line emission spectra. We see colored lines at some places. And why does it observe? Because when the light emitted by the electron falls into the visible region, then it becomes visible. And to which part of the visible region? Visible region like with gear. These colors: violet, indigo, blue, green, yellow, orange, red. And to the visible region where the wavelength matches, such a color is shown in the emission line spectra. This is very important, and hence it has become the most successful model to explain the line spectra. Moving further, Bohr's atomic model successfully explained the hydrogen atom spectra. In the line spectra of hydrogen atom, 5 series were obtained: the Lyman series, Balmer series, Paschen series, Brackett series, and Pfund series. People were quite amazed that hydrogen with only one electron. How can an atom with only one electron can have multiple lines in its line spectra? So Bohr here successfully explained the phenomena. So Bohr successfully explained this phenomena by stating that when we take the sample of the hydrogen gas, there is not only one atom. There are multiple atoms of hydrogens are present. Since there are multiple atoms present in the sample gas, therefore there are multiple electrons. And when electrons are losing energy and are jumping back to the lower energy levels, various series could be observed. When electrons from the higher energy level are jumping back to the first energy level, any electron in the higher energy level, when it is coming back to the first energy level, then such a series was named as the Lyman series. And when electrons from the higher energy state are coming back to the second energy state, then it was termed as the Balmer series. When electrons are coming from the higher energy state to the third energy state, then it was termed as Paschen series. And when the electrons are returning back to the fourth energy level, then it was named as Paschen series. And in a very similar manner, when the electrons from any higher energy state are returning to the fifth energy state, then it was named as the Pfund series. The Lyman series fall in the UV region, whereas the Balmer series falls into the visible region. The remaining three, Paschen, Brackett, and Pfund, three of them are falling under the category of IR region. That was the explanation of hydrogen atom spectra by the Bohr's atomic model, and it was one of the greatest achievement of the Bohr's atomic model. Bohr had successfully explained that why those 5 series, that is the Lyman series, Balmer, Paschen bracket and Pfund, were found in case of hydrogen atom spectra. But when the hydrogen atom spectra was obtained under a very high resolution spectroscope, then it was observed that a single line in the line spectra was splitted into finer lines. Bohr didn't had any answer for this, and that had become the biggest drawback in the case of Bohr's atomic model.